Hello students, welcome back to another video on electricity and magnetism. Today's video is going to focus on electric fields and magnetic fields. So previously we've already talked about the electric force and the magnetic force. In the video, when I was talking about the magnetic force, I already discussed how magnets and moving charges create magnetic fields. Here I've drawn a picture of a permanent magnet which has a north pole and a south pole. The magnetic field is going to come out of the north pole, and those field lines are going to be directed towards the south pole. So all around the magnet there is this loop of magnetic fields where if any other moving charge enters this magnetic field, it will feel a magnetic force. The direction of that force can be determined by the right-hand rule, and I would encourage you to revisit the previous video on the magnetic force to get a better understanding of how magnetic fields, magnetic force, and moving charges are related to each other. Now I want to take some time to talk about electric fields. Whenever I was discussing the electric force, I was talking about how when two stationary charges are some distance apart from each other, there is a force between those two charges that is determined by Coulombs Law, which relates the strength of the force to the strength of the charges as well as distance between those two charges. So let's say I have a positive charge here and then a negative charge here. They are some distance apart. According to Coulombs Law, the strength of the force between these two charges can be calculated according to this equation. Here's my equation for Coulombs Law, which says that the electric force is equal to K, which is Coulomb's constant. K is approximately 8.99 times 10 to the 9th power, and then times charge 1 times charge 2, and then divided by the distance squared. So this is still useful to determine the electric force, but in addition to there being a force between these two charges, there's also an electric field created. Similarly to how magnetic fields are created between north and south poles, electric fields are also generated whenever a charge is present. In the case where I just have a positive charge, no negative charge, there's no electric force being applied to this charge. However, this charge is emitting an electric field. In the case of positive charges, the electric field points outward. Okay, so we use a capital E to notate electric field. So here I can see that all around this positive charge there's an electric field. If another charge comes into this electric field, it will feel the electric force. As we discussed before, the strength of that force depends on the distance, which we can find with Coulomb's law. The concept of electric fields provides us a good visual understanding of how electricity works. Another cool way you can think about electric fields and how it relates to the strength of an electric force. The more electric field lines there are in a particular area, or the more dense the electric field lines are, the greater the force will be if a charge is placed in that spot. So I can see that right next to the charge here, the electric field lines are pretty dense, they're close together. So there's going to be a greater force if I put a charge right there, whereas further away from the charge, the electric field lines are more spread apart, they're less dense. So if I put a charge here, the force between those two charges will be weaker than the force to the closer charge. Now we can ask ourselves, if positive charges have electric field lines that point away from the positive charge, how does an electric field look like for a negative charge? Okay, so positive charges have field lines that go outward, negative charges are the opposite, and they have electric field lines that point inward. Okay, so here's a simple picture of an electric field for a negative charge, where all those field lines are pointing to the center. And the same concept applies with the density of the lines. If I place a charge close to this other charge, it's going to feel a greater force due to the high density of field lines right next to the charge. If I place a charge far away from the charge, it'll be weaker because there's a less dense electric field in that area. This is still consistent with Coulomb's law, which says that the strength of the force gets weaker whenever the charges are separated further apart. Now I'll show you what it looks like whenever we have a positive charge and negative charge next to each other. Okay, so this is what the electric field might look like between a positive and a negative charge. For the positive charge, we still have those electric field lines coming out of it, and for the negative charge, we still have the field lines going into it. But now that they're close together, the electric field is going to shape in a way that these electric field lines will now wrap around from the positive charge to the negative charge. What these electric field lines can tell us is how will a positive charge move if I put it in this electric field. So here I have these two charges already here, but if I have another positive charge and let's say I place it right here, this positive charge at this spot will feel a force that goes this way, away from this positive charge and towards this negative charge. It will sort of follow this motion and wrap around. The opposite is true for a negative charge. If I place a negative charge right here, a negative charge will go the opposite direction of where that electric field line points. So since it's pointing this way, it's going to go the opposite direction. So the negative charge will wrap around this way towards the positive charge, and this positive charge will wrap around this way towards the negative charge. So that's another way we can think about electric fields and what impact they have on surrounding charges. Now I'll show you one last example of what electric fields look like between two of the same charges, so two positive charges or two negative charges. Okay, so if you have two charges that are the same charge and that are placed next to each other, those field lines will avoid each other and they will bend away from each other. These electric field lines always want to come out of a positive charge and go into a negative charge. So it makes sense that the field coming out of this one doesn't want to go into that one because they're both positive. And this makes sense because we know that like charges repel each other. So if I place another positive charge somewhere in this electric field, let's say right here, it will be repelled from both of these charges and it will get pushed away from them. So in this case, downward. If I put a negative charge right here, it's going to go the opposite direction of that field line. So it's going to go towards this one. So that's the general gist of how electric fields work for single charges and pairs of charges. There's one last thing I want to talk about that relates to magnetic fields and electric fields, and that's called induction. So as electricity and magnetism are closely related, they can also influence each other and induce each other. There are various inventions now that operate off of induction, such as generators, motors, and transformers. I'll talk about those devices tomorrow. To keep things simple for now, induction involves a change in either an electric field or a magnetic field and what that change does. So induction can occur when there's a change in a magnetic field or a change in an electric field. When there's a change in a magnetic field, it induces an electric field. When there's a change in an electric field, it induces a magnetic field. So whenever there's magnets that are moving, there's a changing magnetic field that creates an electric field. Whenever there are charges moving, they induce a magnetic field. So they both induce each other if they are changing. This is the principle that makes light possible, because light is an electromagnetic wave, which is in an electric fields and the magnetic fields that are constantly changing, and as they are changing and looping around each other, they induce each other in a way that they can keep propagating forever. So although electricity and magnetism can be said to be two distinct forces, they're actually really one and the same force. They are the electromagnetic force, and they are really more closely related than people often believe. I hope this video helps you guys understand electric fields and magnetic fields a little bit more, and how whenever those fields change, they induce the other one through induction. Okay, that's all for today's video, guys. Thanks. See you next time.